When a seed violently cracks open and extends its first tiny leaves toward the light, it is triggering an intense burst of localized biochemistry. On this scale, 1 gram of microgreen tissue contains the exact same vitamin and polyphenol density as 40 grams of mature vegetables. We assume plants shed vitamins as they age, but this variance is driven by a phenomenon called the dilution of maturity. Understanding how plant nutrition actually scales requires us to stop looking at species classifications and instead examine the precise moment a plant is harvested. A plant's complete biological and chronological development from a tiny seed into adult vegetation is called its ontogeny. By tracking how a plant allocates its physical mass across this exact timeline, we can locate where nutrient density peaks. Biological growth forces an economic trade-off. A developing seedling operates on a strictly limited budget of metabolic energy, and it must choose whether to invest that energy into synthesizing complex chemical defenses or building physical size. This suggests that nutrient density is inherently linked to developmental timing, forcing us to track the chemical composition of each growth phase. This blank Cartesian space will map the total physiological mass of a plant across its developmental stages. We start at the cotyledon stage. This is the precise moment the seed deploys its initial biological resources. The seedling must establish immediate viability in a hostile environment, deploying an initial package of chemicals that acts as a survival kit. This payload is highly concentrated. It consists almost entirely of tightly packed bioactive compounds, specifically dense concentrations of polyphenols and vitamins. The plant synthesizes these specific compounds because they are strictly necessary to jumpstart early metabolic functions and establish immediate cellular defense mechanisms against pathogens. Without having initiated physical expansion, these complex defense chemicals remain confined within a microscopic volume of tissue. Compared to the negligible total mass of the tiny seedling, this dense chemical payload accounts for a heavily significant percentage of the plant's overall weight. The cotyledon stage represents a transient period of peak biochemical efficiency before the plant initiates physical expansion. Moving past the cotyledon phase, the plant inevitably pushes out its first true leaves. Here, biological priorities shift. Chemical survival is deprioritized in favor of generating vertical structural scale to capture sunlight and outcompete surrounding vegetation. To achieve physical size, the plant relies on turgor pressure, constructing massive intracellular vacuoles filled entirely with heavy water to keep cells rigid. To support that expanding water weight, the plant must simultaneously generate a sprawling network of thick, fibrous cellulose walls to maintain upright scaffolding. Crossing into maturity forces the plant to aggressively divest from dense nutrient synthesis, pouring its biological budget into raw physical scaffolding and heavy water storage. This stacked area chart reveals how internal composition reacts to that biological shift as we move down the ontogeny timeline. Our base layer represents the mass of nutrients, polyphenols, and vitamins. Over time, the synthesis rate flattens, keeping this layer slow and steady. Stacking the required water mass on top of those nutrients yields a curve that angles violently upward in an exponential trajectory. Above that, we map the fibrous cellulose mass, expanding aggressively in volume to physically support all of that rapidly accumulating water weight. Looking at the contrast between the base layer and towering upper sections, water and fiber clearly grow to account for the overwhelming majority of the plant's bulk. This data proves mature vegetation functions as an enormous, waterlogged architectural scaffolding system. As the plant rapidly scales upward, the explosive increase in raw structural biomass completely outpaces the plant's slow, flatlining rate of nutrient synthesis. This visual equation shows the rigid stoichiometry at play. Tissue density equals absolute nutrient mass divided by total plant mass. That total mass denominator breaks down cleanly into 3 components: nutrient, fiber, and water mass. Applying the data from our ontogeny timeline, we see the fiber and water variables in the denominator expanding rapidly. The mathematical consequence is unavoidable. As the denominator experiences an immense exponential increase in structural weight, the resulting density quotient inevitably plummets. The polyphenols and vitamins did not vanish from the mature leaf. They were simply heavily diluted by a massive influx of cellulose and water. The 40 times discrepancy in nutrient density emerges as a rigid mathematical consequence of an exploding structural denominator. Returning to this split-screen scale, we can test this math against the 40-gram tower of mature leaves. If we apply a filter to mathematically strip the 40 grams of mature vegetation, starting by dissolving the heavy water mass, and then apply a second filter to strip away the sprawling fibrous cellulose scaffolding, we isolate the raw nutrient payload. Once the dilution variables are removed, the isolated nutrient mass of the mature plant is visually identical to the single gram of microgreen tissue. The sheer, massive physical size difference between adult vegetation and a freshly germinated seedling is almost entirely an illusion constructed by heavy water and structural fiber. Harvesting a plant precisely at the cotyledon stage is a highly calculated, deliberate intervention in its biological ontogeny. This intervention targets the exact biological window where the survival payload is most concentrated, striking right before the delusion of maturity begins. Traditional agriculture demands waiting for total physical maturity, inherently subjecting the final harvest to a massive biomass penalty caused by required structural growth. By completely bypassing the sprawling physical scaffolding required by adulthood, microgreens isolate and extract a plant's peak biochemical efficiency, accessing the highest measurable levels of natural nutrient density.